Okay. So, we discuss so far the thin cylinder. Now, we are going to discuss about the thick cylinder. So, I mentioned already the what is thick cylinder? The cylinder which where the diameter by thickness is less than 20, right. So, thin cylinder means where we had the diameter, remember the inner diameter by thickness was greater than 20, greater than or equal to 20 was a thin cylinder. Okay. Now, we are going to see there will be situation where you need to provide the bigger thickness of the cylinder, wherein your d by t ratio you need to it will be less than 20. Then all the theories what we discussed so far will not work out. Okay. That is very important point you have to understand. Then we categorize that particular cylinder to be a thick cylinder. Okay. So, the inner diameter by, please remember I am mentioning again the inner diameter, not the outer diameter, not the mean diameter. Inner diameter by t should be less than 20 to call it as thick cylinder. So, as we discussed previously also that in general any pipe sections, because of the internal pressure we have a hoop stress which is radial in direction, right, radial in direction and tensile in nature. Okay. Please remember this is tensile in nature, and the longitudinal stress which is along the length of the cylinder. If this is my cylinder, right. So, this is in this longitudinal direction sigma L we called it at, right, longitudinal direction, that is again in tensile in nature, right. So, tensile in nature sigma L. So, again this is in tensile nature. I mentioned already the very first class in cylinders, right. This was a sigma C, which is your hoop stress. Now, the third one which is the radial stress, again this is all three stresses are perpendicular to each other, I told you, right. So, this is exactly perpendicular to that which is from center, it is radial direction, right, radial direction, radially, right. So, now I mentioned that this is in the compressive nature, very important. This is in compressive nature, because well in derivation you will have to realize this matter. Okay. Please do not forget the radial stress is a compression, radial stress is a compression. We can also say radial pressure or radial stress. Okay. So, we may call it as this is P x at any distance x from the center. So, because the thickness is much larger, not much larger, its thickness is larger compared to the thin cylinder. So, we cannot neglect the radial stress. Okay. Sigma or P x or P r is not neglected, which is neglected in case of thin cylinder, because thickness is too large. The stress here, stress here, stress here not the same, is varying. That is the meaning. The radial stress or radial pressure is changing from inner diameter to the or inner radius to the outer radius. Like that is the part you have to see. And another important understanding that this the longitudinal stress is constant. So, sigma L is constant. It is constant because of the strain is constant. Because strain is constant, the stress is also constant, because stress is proportional to the strain, right. That is what we learnt it. So, this is these two things we have to understand in the thick cylinder. The strain is constant, so the stress is constant, which is longitudinal, Okay. And the then the hoop stress sigma c and radial stress which is sigma x, which is all called px or pr, whatever. X is because simply from center any distance in the within the thickness, we call it as, let us say, distance x, the px, okay, or pr. Some books write pr, somebody writes px. So, these are not constant or varying parabolically. Parabolic variation within the thickness, which you need to understand. Okay. So, if you understand this, we will go further. I mentioned this sigma r, a radial stress, or sigma x, you can say anything, is the large in thick cylinder, hence cannot be neglected. It is constant, I mean this is sigma r. Okay. So, the which radial stress was very small, we neglected in the thin cylinder. Sigma c is a hoop stress which is not uniform across the thickness, right, across thickness, which is not the constant, varying, okay, not uniform. This is what I already mentioned. And sigma r is a PR, anything is also pressure, not a load, is compressive nature. Compressive nature, you have to understand. Why I am saying, you will understand later on. And sigma c and sigma l, hoop stress and tensile, longitudinal stress are tensile in nature. Okay. So, now our aim is to work out this radial stress sigma r or PR, radial stress is we need to work out, and hoop stress, how much is hoop stress, how much is the radial stress, is to be derived now based upon the Lamb's theory. So, Lamb's theory is used here to find the radial and hoop stress. I right now I would like to call is the Px, and hoop stress is sigma c, we already know. Okay. So, now, so what I am doing is I try to understand that if I have a cylinder like this, a cylinder, right, and it has got inner diameter is, sorry, okay. So, this is the thickness T, right, thickness T. So, what I call that, I would like to call the inner radius is your R1, outer radius is your R2, right. So, R2 minus R1 becomes the thickness, right, that we should understand. R2 minus R1 becomes the thickness, okay, that point. Now, what I do, I would like to take a small ring within the thickness, sorry, because I want to derive, I will take a small ring, okay. I want to take a small ring within the thickness, okay, within the thickness. I will draw separately that ring alone here. I am going to draw separately the alone. So, this thickness is my, let us say that particular ring from the center at a distance of x, from center, that is the radial distance, please understand, the x is not a linear distance, it is a radial distance x, and the thickness of this ring is dx, very small ring I want to consider, which is dx thickness, with the ring is at a distance of r from the center. Okay. Please understand. So, what is R2, which is your external radius, and r1 is your internal radius, okay, and the x is the distance of the ring from center, okay. Then dx is the thickness of the ring, thickness of ring, okay, thickness of the ring, okay, that is all. So, assuming that let us say P x is the radial pressure or radial stress, which is I want to work out, and sigma c is hoop stress. So, knowing these parameters okay, knowing this parameter, we would like to derive these two things, the radial pressure or radial stress and sigma c hoop stress. These two things I want to derive. So, let us go to next. Anyway, this. So, what I do, I will try to draw that ring longitudinally. I will take the half of this particular ring, half of the ring, and I will take the longitudinal portion of that. Okay. So, what I have done? I have taken the same ring with a length of L. I took a length L of the cylinder, right, and the thickness is equal to dx, right. Now, I know from center what is this distance, which is x. The ring from the center is x. So, this side again, this is since radius, this is another x, which is total is 2x. Okay, you have to understand this. Now, the pressure acting, the radial pressure acting is P x in the ring. Okay, you understand this. This ring has a diameter of 2x, that meaning, so acting with the radial pressure of P x from inside, right. This ring has a thickness of dx, and I took a length of cylinder of L. Now, if you try to carefully see, the stresses acting here is your hoop stress, which is tensile circumferential stress, which is sigma c, right. Now, if you look at carefully, this particular ring, I told you, if I look at the cross section of the same ring, okay, cross section of ring. So, there is on this ring, sigma c is a hoop stress acting, internal pressure is your P x, and on the ring there will be pressure from the outside. It is because of the radial pressure varying within the thickness. So, this stress is your P x plus d P x. So, this is a pressure acting on the ring from outside. This part you should understand. Okay. So, if you know this, you understand this. Okay. Now, let us write down what is the situation where it burst. One point of time it will burst. So, the bursting force, right, any because the cylinder may fail at a given situation. So, when the bursting force is a force from the inside, right. So, that one is because of the internal pressure, which is P x into P x is the internal pressure, which is radial pressure, internal pressure P x into, we have 2 x is the total length inside where the pressure acting into the length of the cylinder is L. This is a force, right? Pressure into area, right? This is internal. Now we can see on this cylinder, I also said there is a external pressure, which is again the pressure because of the variation stresses within the thickness, which is this, right. So, which is, and this is going to be the opposite side. So, I will say minus the p x into 2 x is your upward, right, and p x plus d p x is a downward pressure. So, I will write down p x plus d p x into the area on which it is acting, which is the downward, which is 2 times x plus dx into again length. Okay. So, that is the x plus 2 x, which is the little outer thickness, so it is outer area, right. It is outer area L, this is L, right. So, L and x plus 2 x, x plus dx is the outer. Okay. So, this is the bursting force. So, if you simplify this, what happens? P x 2 x L minus, or you can take a common 2 x and 2 L, because 2 L here is there, here also 2 L is there. So, if I take a common 2 L, if I take common, what happens here? P x minus p x into x will be there. So, let us say x p x, right. So, now multiplying each of the term here. So, p x into x, x p x, or let us not have minus, everywhere it will be there, then x p x, then minus dx p x, the next term which is minus x dpx minus dx dpx. Okay. This is a bursting force, we simplified simply, but if looking at the quantity dx is very small dx, which is the thickness of the ring, and change in pressure within the thickness is dpx further small. So, two small quantities, multiplication is further small, we know that. So, then we neglect it, okay, taking to be 0. So, what I get, right, neglecting that. So, x p x and x p x get cancelled here. So, what I get it finally is the 2 L into, since minus is there, I will take minus common, minus 2 L into x or dx px plus x dpx. So, this is my bursting force. Now, this bursting force has to be resisted by something else. So, the bursting force will be resisted by the Hooke stress sigma c, right. So, this has to be resisted by the radial this circumferential stress, which is Hooke stress. So, I will write down that stress, right. So, the resisting force, right, the resisting force is nothing but my Hooke stress into the area on which it is acting, is it not? So, that is nothing but your Hooke stress. How much Hooke stress acting? Which is sigma c and sigma c, twice sigma c into onto the ring, right. The ring is length of how much is the, what is the length of ring, which is dx, the thickness of the ring is dx and length is L, right. So, dx into the length, because dx is very small, we can almost say a small thickness into the length will be my resistance to force. So, equating these two, what happens? When I equate these two, so what do we get? Let us say use another pen. So, 2L sigma c is equal to minus 2L dx px plus x d px. So, 2L get cancelled. So, I get sigma c equal to, what I am going to get? The sigma c equal to, right, sigma c equal to, so minus px minus x dpx by dx. I hope this is clear. This is a hoop stress, I got it. In terms of the radial pressure at distance x from the center, this is the equation I got. Let us say this is equation number 1, I got it. Okay, please remember this. Okay. So, I also want to know the radial pressure, but now there is a relation between radial pressure and hoop stress or radial stress. Now, one more important understanding I have, the understanding is that, what is understanding? That the strain along longitudinal direction, strain in longitudinal direction in the thick cylinder is constant, right. That also means stress in longitudinal direction also constant. That is what important understanding. This implies, this understanding comes from assumption that the cylinder cross section remains plane even after your applied stress. The plane remains plane, the cross section remains plane before and after the stress applied, right. That is very important. So, that means the strain has to be constant, that means stress has to be constant, because stress is proportional to strain. Okay. So, now what is your longitudinal strain? By formula, as per formula, what is longitudinal strain? So, longitudinal stress, sorry, L, sigma L by Young's modulus, is it not? Stress by Young's modulus is your strain. Now, minus, because it is two dimensional body, right, it's a cylinder is two dimensional body, right. I mean, the if you look at the surface of the cylinder, it is two dimensional, right, and the other direction will get reduced strain, which is your hoop sigma c by E, right. Hoop strain will have tensile, so minus, because that is going to reduce, diameter hoop strain is going to reduce, which is mu times, right. Now, I am going to write something here which you have to understand, plus mu times px by E. Why this plus came here? This plus because positive, because px is compressive nature. When there is compressive, what happens diameter or what happens to strain? Strain increases, because of the compression strain increases, I mean the lateral direction. So, lateral direction increase, that is why positive. The hoop strain lateral direction reduces, so is minus. That part you have to understand, that is the difference. That is why the compression, the radial pressure is compression. Okay. So, if you understand this, and this we said is going to be constant, the strain is constant in longitudinal direction, we want to say. And since we said the stress sigma L, the longitudinal stress also constant, that means since E also constant for a material, so sigma L by E also going to be constant, right. Then what can I write? I can write this entire thing to be, I can write this to be mu times minus mu times sigma c by E plus mu times p x by E to be a constant, is it not? So, this also constant. So, adding there becomes another constant, right, and since E also constant, so other multiply with the constant becomes another constant, mu also constant, right, taken in common and divide with the constant becomes another constant. So, please understand this, okay, understand this. That means what? So, basically is your sigma c minus sigma or sigma p x. P x is another constant. Of course, I am taking minus common, and the minus of the constant becomes another constant, right. This is a constant. See, there are so many constants business are coming. Okay. So, finally, sigma c minus p x is a constant. Okay. So, that constant I assume to be a 2 times a. I am assuming. You may say, why do you assuming 2a? That does not matter. You can assume anything. 2p. 2d, 2c, 2d, assume any constants. You can assume a also, right? But 2 has some significance here. So, we assume it becomes easy for the calculation, that is all, nothing great about it. Okay. 2a is a constant, understand. Now, that means what happens to sigma c? The sigma c is nothing but p x plus 2a. Remember this. Okay. Let us say this is equation number, let us say 2, we remember this, very important. Now, so we also got one sigma c here, right, some equation 1. So, these two must be same, right. So, I will bring it here, that is minus p x minus x dpx by dx is equal to p x plus 2a. Okay, from equation 1 and 2, equating this. Okay. So, equating this came from equation 1 is equal to equation 2. Okay. So, what happens here? So, bringing this p x this side. Okay. So, what happens? 2 p x, right, 2 p x, this bring p x this side, 2 p x, take the minus negative other side, 2 p x equal to x dp by dx, and bring this remains here, 2a will remain here, right. Sorry, this is I am taking this other side. So, this minus p x taking that side. So, we will have a negative here, okay, no problem. 2 p x, this will remain negative here, this remains a negative. Okay. So, now that means p x. So, this minus p x comes 2 p x. So, 2 p x plus 2a is this side, left hand right hand side remains. So, this left hand side will be minus p x dp by dx. So, let us take the dx terms and x terms one side, that is like a partial differential equation, right. So, what we do? Variable separation method, right. So, variable separation method, wherein, so what I do? So, I have dpx by px plus a. So, 2 get cancelled there 2, okay. I mean the 2 not cancel, go to other side. dpx by px plus a will be equal to minus 2 dx by x. This is how I separated, variable separation method, because dpx here px, dx x. Now, integrating both sides, what happens? Integration of that, right. So, integration dpx by px plus a equal to minus 2 integration dx by x. So, what do we get here? This is your log, right, log p x plus a, log p x plus a equal to minus 2 log x to the base e, right, plus c, some constant you have to write. So, that constant I am going to write as log b to the base e, right, is a constant. For me, log b to the base e is a constant. In the integration you used to use c as a constant, the c nothing but my log b to base e. So, then arranging these terms I can write as log x square, right, minus plus log b to the base e. So, this again I can write down as log b by x square, because minus term, okay, go to denominator, b by x square. So, now comparing the other side, both sides, now I can just take anti-log on either side. So, what I get, p x plus a is equal to b by x square. So, that means the p x equal to b by x square minus a. So, this is what your radial pressure, okay, radial pressure or radial stress at a distance x from the center, very important, at a distance x from the center. That means, is a parabolic varying something like this. If it took the thickness here, outer diameter this, inner diameter this. So, let us say this is a distance somewhere at here, at x here, this is your r1 and this is your r2. So, inner at a distance x, inner side at r x is equal to r1 is maximum, right. When it goes to the outer side, it is going to be minimum, maybe 0 or minimum, you do not know, okay, it is going to reduce like this. So, this is a stress, parabolic variation of stress. So, this is what I am we are saying, the stress variation in the pipe, maximum in the P max in the inner side and P minimum in the outer side. This is a variation of the radial stress within the thickness, is not going to be constant across the thickness. Okay. Now, this is the p x, right. Now, what is the sigma x, sorry, sigma c, which is the sigma c, which is a hoop stress. So, we know the hoop stress is nothing but sigma c already worked out, right. The sigma c is equal to p x plus 2a, right. Now, substitute here the sigma c equal to p x is nothing but b by x square minus a plus 2a. So, becomes how much, b by x square plus a. So, this is your sigma c. Okay. Again the summary, I will write down sigma c is a hoop stress. Hoop stress is equal to b by x square plus a, and hoop radial pressure p x is equal to b by x square minus a. This is what we derived. That is all, our derivation is complete. Okay. So, the question comes, what are these a and b? So, a and b are the constants, can be derived from the boundary conditions, right. These are the boundary conditions. So, what are the boundary conditions? The boundary conditions are now you can look at carefully the cylinder. Okay. So, from here this is your r1, this is your r2 outer radius, right. So, this x means from here anywhere here x, in within the thickness, that was x. So, x is varying from r1 to x varying from r1 to r2, x varying from r1 to r2, right, starting from r1 to r2. That part you have to understand carefully. Now, at x is equal to r1, that means inner radius. At inner radius inside of the cylinder, the pressure, the radial pressure Px is equal to P naught, or whatever pressure given to you, or fluid pressure given to you, okay, fluid pressure given to you. And using this one of the boundary conditions, at x is equal to r2, that means at the outer radius the radial pressure is equal to 0, outer pressure is 0, the radial pressure outer surface of the cylinder is 0, or maybe atmospheric, sometime at most atmospheric pressure compared to the your pressure inside fluid is so small, so you may neglect it, make it 0, or sometimes you will want to consider, you can consider atmospheric pressure. Okay. So, if you have two boundary conditions, means two equations, using two equations here, use this in the Px. I am not talking about the Hooke stress, I am talking about the radial pressure. Okay, use the boundary condition in the radial pressure, and two boundary conditions, two unknowns, I can find A and B, and once we get A and B, put it in Hooke stress and put it in radial pressure, and you can get the both stresses, radial stress and Hooke stress. Is this clear? Any doubt here? So, I would like to stop. If you have any doubt, you can ask me.